I rattled it off for you guys last time, but I didn't derive it. I think I owe you some kind of explanation for that. So let's see here. Kinetic energy in non-Cartesian coordinates. So let's start out with the polar case. Suppose you've got r and theta functions of time, right? Of course, we also know the relation between x and y, right? And so we know it's, I mean, sort of my, at least here's how I thought of it as a physics major. I'm not sure this is most optimal. If I was more clever, I'm sure there's another way to get to this, but here's an unclever way to think of it. You just take the derivative of both of these, and you have product rule, right? So like x dot is r dot cosine theta minus r sine theta theta dot. And y dot is r dot sine theta plus r cosine theta theta dot. One of the things that this lecture implicitly answers for you is why people use dot notation. Do you see why? It's right in front of you. It's so much easier to use this notation as opposed to the prime notation for these problems. In my opinion, but maybe it's my upbringing. So what's x dot squared plus y dot squared? Think about it. You've got an r dot squared. You've got a cosine squared theta plus sine squared theta from these guys. Then you've got plus 2 r dot theta dot sine theta cosine theta. So you get this times this times this, minus to start with, and then you get it with a plus. I don't really need to write this down because these cancel, the cross terms cancel. And you're also getting what? Plus r squared sine squared theta plus cosine squared theta, theta dot squared. So the cross terms cancel, right? And what you're left with then is x dot squared plus y dot squared is equal to r dot squared plus r squared theta dot squared. So the speed squared in 2 dimensions you can either write as the square of the Cartesian velocities or the polar velocity plus r squared times the angular velocity squared, actually. Theta dot is omega in usual physics 231 language, right? So what does the Lagrangian look like? What's the Lagrangian look like in polar coordinates then? Yeah. So let's talk about m in the plane under force which is radial, or you could say central. So the force acting on m can be written as a function of r, and it's a conservative force. We'll assume it's minus du dr, okay? U is the potential energy is just a function of the radius. Let's just suppose that. What's the Lagrangian? Lagrangian 1/2 m v squared minus u of r. But let's see here. What is that actually? Indeed, r dot squared plus r squared theta dot squared minus u. So then what are the other Lagrange equations? Well, before I get to that, what's partial L partial r dot? And what's partial L partial theta dot? Sorry if I'm in reruns. I might have said this last class. mr squared theta dot, yeah. This is not an accident. This is the momentum in the r direction. This is the so-called angular momentum, or usually I use an L. Or, I mean, you could call it p sub theta, but when theta is not a linear coordinate, it's an angular coordinate, this is the angular momentum. You might remember that the moment of inertia is mr squared for a point particle, and so what you have here is p theta is equal to I omega. Maybe you remember that. The Lagrangian treats the linear momentum of the radius and the angular momentum of the angular coordinate in the same theoretical setup. There's not, here's my linear mechanics, here's my rotational mechanics. There is just mechanics. Lagrangian mechanics, the true mechanics. Since about 1780. So, what are the early Lagrange equations? Well, partial L, partial R is equal to ddt. I'll tell you, I'm going to start with the theta. Partial L, partial theta is equal to ddt. A partial L, partial theta dot. What does that give me? What's the theta dependence? Yeah, 0. 0 is equal to ddt of mr squared theta dot. In other words, angular momentum is conserved. Yeah, we have conservation of angular momentum here. Because the force is central, it doesn't change the angular momentum. And then the other equation is what? It's just the minus partial u partial r is r double dot. In other words, it's the radial force is equal to the mass times the radial acceleration. So if you can prove that the force of gravity makes the motion go in a plane, right? Which you can do through a little vector calculus argument, because if you have a gravity force it acts along the line connecting two things. If one of the things you put at the origin, then you can prove that the torque is 0, r cross f is 0. The torque being 0 is basically the binormal's constant is what it boils down to if you look at the Frenet-Serre geometry of it. And so you can, not too hard to prove that the motion's planar for like the gravitational force. So once you know that, you can put polar coordinates in the plane, and then you do this derivation essentially, and then that would show you that angular momentum is conserved. Now there's a big cheat there. I'm assuming that you can put one of the, if you have two bodies gravitating, right? You can't really put one at one point in space and fix it, can you? It actually moves around. So that's a cheat, that I'm assuming that you can put the sun at the center and it's at the origin, and then we can just look at the distance from the origin out to Earth or whatever planet you're studying, right? That's a cheat. So there's a natural question to ask is like, can you get around that? Can you solve the so-called two-body problem? Do you guys know what the two-body problem is? You're saying you take two bodies like M1 and M2 out there, say 3 dimensions. It isn't 3 dimensions. I mean, this is physics. It's 3 dimensions. Right? And then you've got two bodies, and then you have to have some interaction between them, right? So here's the usual question: is suppose that they're interacting under something called a central force. What's a central force? Central force is one that acts along the line that connects them, like that. It has to act in that direction, all right? So like the force of 1 on 2 would have to be like this, or like that. It could be repulsive or attractive, but they also have to come in the third law pair, right? I mean, Newton's third law applies. So if M1 puts a force on M2 like that, then M2 has to put a force on M1 like that. But if it's a central force that is governing the interaction between these, It has to be along the line that connects them, and it can only depend, the only dependence possible is on this distance between them, which you might call, well, I would call it, it's the magnitude of R1 minus R2. If you take, say, the position vector to R, that one is 1, and, oh, I can't. So let R1 and R2 be their position vectors relative to some common origin. So that the force that acts on them, one on the other and the other on the one, can only depend on the distance between them, and it has to act in the direction connecting them. That's a central force. They're moving around. So you kind of need to know the answer before you did that to do what you're saying.
So
this problem can be solved.
If you did that, then you integrate it over time where you get different positions.
Mm-hmm.
At every moment in time, you get all of the little superpositions at every little position added together in your integration.
I don't know. I mean, I don't know.
Essentially, mechanics figuring out what they're doing to each other at every t and every point x, y, and z.
Yeah. Well, if you guys would like, I can show you the solution to this problem next class. What's that? You'd like to see that? Yeah. Okay. I'll work the central force problem out next class. So you have that waiting for you.
Even like two dimensions, like electromagnetic force right now, and they're talking about like how they have two particles, and if they're like moving in space, you have to like split them up. How to solve it? That in three dimensions.
Right.
I refuse to believe that you can't.
No, this can be solved. This has been solved since about Newton. I'm not sure if Newton solved this or what, but I mean, this I can solve this for arbitrary. Well, I can find the Lagrange equations in a nice, clean way for arbitrary central forces. For the case of the force of gravity, or no, I think you can find something called an orbital equation for essentially arbitrary central forces. And in the case of Newton's universal law of gravitation, it can be explicitly solved. The solutions are conic sections in polar coordinates, using polar coordinates in the plane of the orbit. It'd take me about a half hour to work it out. Now, that said, it's pretty well known and famous that if you ask the same problem for three bodies, at least at the moment, no one has a general solution. For special situations, you can solve the equations of motion. There are certain, like if you've got two binary stars, for example, rotating around each other, and then you've got a third thing that's kind of like going whoop, 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 or something like. I mean, there's special solutions that are known here and there for the three body problem, but generally speaking, it's been tried for a while. No one can crack it. But two you can solve in general. Two is much easier than three in this case. But the larger point here I wanted to get across to you is you're starting to see that you can use other variables than Cartesian variables for the variables in the Lagrangian. Generically speaking, you think about these so-called generalized coordinates. The physicists usually use like q1 through qn for them, and their velocities q1 dot through qn dot. They can be linear coordinates, they can be angular coordinates, they can be weird stuff you'd never even thought about. But the point is, in physics, is if you can write down this Lagrangian, which describes the motion of something essentially, then you can find the Lagrange equations and analyze it, and that's kind of it. Now, I've asked you some homework problems. Everything I've done today so far has been, I would call them problems in free space. The next thing that you would think about is how would you do like the Lagrange problem on a surface or something? There are two approaches. Suppose I wanted to solve the Lagrange problem, but it's constrained to a surface. And that surface, suppose the surface is x plus y plus z equals to 7. Happy? Okay.
Not a variable.
Not a variable? All right.
Unless it's a four-dimensional plane equal to 0.
So if you have that, it's not really a three-dimensional problem anymore, right? It's a two-dimensional problem. And there are two ways to solve this thing. The one way is to say, I'm going to throw out one of my variables and just treat it as a two-dimensional problem from the start, right? And if you do that, then you've got something like this, right? So if you were to do that, you could say, well, if I'm going to solve something on this plane, I'm just going to keep x and y. And I'm going to say z dot, right, is minus x dot minus y dot. And so what would the kinetic energy be in this case? It'd be 1/2 m, x dot squared plus y dot squared plus x dot plus y dot quantity squared. That would be the kinetic energy on that plane. And you can go from there. There's another way to do it called the method of Lagrange multipliers, where you keep three variables for the Lagrange equations, and you add another variable called lambda, and you take the Lagrangian. I would take L that you would usually use, and then you subtract minus lambda times x plus y plus z minus 7. So you just take the Lagrangian, you add this term onto it, and you treat it as a problem of four variables, where you have the x, y, z variables and this extra so-called auxiliary variable of the Lagrange multiplier. The Lagrange equations for the multiplier are just the constraint equation, because it's not dynamical. There's no lambda dot. So the velocity of lambda is automatically 0. So the Lagrange equations are just algebraic for the lambda variable. Anyway, I'll try to show you more of this next class, because I've asked you a homework problem about this kind of thing. They're actually very simple. So this is not simple. It's not that hard either, though. It's just you have to make the right choice of notation